In this paper, we propose a framework for local path planning and steering that can be easily extended to perform high-level behaviors. Our framework comprises three phases: the sensory, affordance, and decision phase. First, information from the environment is represented in an egocentric manner known as egocentric perception fields. Affordance fields are used to quantify the relative strength of each possible action. We call these strengths affordances. Finally, the actions having optimal affordance values are chosen as the control outputs. Our steering framework uses speed and direction affordance fields to make a steering decision. Our discretized model uses a network-based architecture having variable resolution. The static field represents the configuration of the obstacles in the environment surrounding the agent. Dynamic fields store the current and future state of the dynamic threats, implicitly taking into account time. A speed is chosen that minimizes the dynamic threats immediately around the agent. These fields are combined to compute spatial affordance fields, which is then used to choose the next direction of motion. Our system can successfully handle a variety of scenarios with crossing threats. Oncoming threats are also successfully handled by our system. Implicit spacetime planning allows agents to predict potential threats in the future and plan their paths around it. The following simulation demonstrates the ability of agents to travel along a curved path to the goal. More complicated scenarios having a combination of oncoming and crossing threats in the presence of obstacles are successfully tackled. An agent passes through a group of other agents in order to reach its goal. Agents have to take evasive actions when encountering another agent at a sharp turn. An agent slows down, allowing the other to pass through a narrow doorway, which only has room for one. Lane formation emerges as oncoming agents maneuver through a narrow passageway. Overtaking arises when a fast-moving agent finds itself behind a slower-moving one. Bottleneck situations arise when multiple agents enter or exit through a single narrow doorway. Queuing is exhibited in these simulations as agents wait for others to pass through. The hallway scenario demonstrates a multitude of agents traveling in opposing directions. Our system is stress tested in large, obstacle-laden environments with as many as 5,000 agents. We observe that exhaustive testing of basic one-on-one and group interactions scales successfully with increase in complexity of environment and number of agents. An urban environment with large buildings is populated with 500 agents. 5,000 agents with random initial positions and goals are also demonstrated. High-level behaviors can be easily integrated into our system. Lane formation is observed when agents queue up politely as they near the goal. A set of agents exhibit snake-like motion as they weave around a set of obstacles. Group persistence is exhibited when two groups of agents travel in opposite directions.